Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome back. Today we are taking a deep dive into, one of the most explosive fields in all of science. I'm talking about exoplanets.
It really is incredible to think about.
I mean, just 30 years ago, if you think back, we weren't even sure if there was a single planet out there, outside our own little solar system. It was all just theory.
Purely theoretical. And now, the pace of discovery since that first confirmation back in '92 has just been exponential. It's almost hard to keep up.
So what's the count now? Where do we stand?
The official catalog, the list of confirmed worlds, is now over 6,000.
6,000.
6,000 separate planets that we know for a fact are orbiting other stars. And that's just in our little corner of the Milky Way.
That number is it's staggering. But as we always talk about on here, finding them is really just step one, isn't it? The real challenge is figuring out what they are.
Exactly. What are they made of? Do they have an atmosphere? And if so, what's in that atmosphere? That's the Holy Grail.
And that's why today we're focusing on this small, but honestly incredibly clever mission that's designed to solve the single biggest problem we have in answering those questions. We're talking about the Pandora smallsat.
Right, and Pandora's in the news right now because it's just hit a huge milestone. It's cleared its final checks. It's ready to go.
It's basically sitting on the launch pad.
It is. And the team lead, Daniel Lapie, says it's about to open and I'm quoting here, a new chapter in exoplanet science.
And what's so interesting is that new chapter isn't about finding planet number 6001.
Not at all. It's designed to do something much more subtle and, frankly, much more important. It's designed to fix a really messy problem with the data we already have. It's basically a cosmic data cleaner.
Okay, so let's get right into the nuts and bolts of this mission, because you said it's imminent. How soon are we talking?
We are talking days. The satellite itself, which is wonderfully described as being about the size of a refrigerator.
A household fridge, I love that.
Yeah, just a normal fridge. And that fridge has been mounted inside a SpaceX Falcon 9 rocket. The hardware is ready.
Okay, so for anyone listening who wants to follow along, when is this happening?
The launch window opens this Sunday, January 11th. It's going up from Space Launch Complex 4E at Vandenberg Space Force Base out in California.
And what time?
It's an early one. They're targeting 6:19 a.m. Arizona time, which for folks on the East Coast is 8:19 a.m.
And I assume we can watch this live.
Oh, absolutely. SpaceX will be live streaming the whole thing, so you can watch this fridge-sized satellite begin its journey.
So that's our mission for this deep dive. A small satellite born out of a university project, hitching a ride on a massive rocket, all to decode the air on alien worlds hundreds of light years away. We need to understand how it works, why we so desperately need it, and how it's sort of the missing link between just counting planets and actually understanding them.
That's it. It takes us from quantity to quality.
So to really get what makes Pandora special, we have to start with its official title. It's a small sat. And it was chosen for this NASA program called the Astrophysics Pioneers.
Right, back in 2021.
So when we think of NASA, we think of these huge multi-billion-dollar, decade-long projects like the James Webb. What does being a pioneer mission actually mean?
It's a really different philosophy. The whole point of the Pioneers program is to be fast and focused. They're much quicker to get from the drawing board to the launch pad.
So a few years, not a few decades.
Exactly. And they have strict cost caps, so they're a fraction of the price of a big flagship mission. The whole idea is to let NASA address these exciting new science questions that pop up without having to wait for a 10-year planning cycle.
It's like NASA's rapid response team. A specific urgent problem comes up, and they can greenlight a smaller, more nimble mission to go solve it.
That's a perfect description. And Pandora is the perfect fit for that model because this problem it's solving, getting clean atmospheric data, has only recently become the #1 roadblock.
Why now?
Well, because missions like Kepler and TESS gave us this massive flood of planets. Suddenly we had thousands of targets, but we realized the data we were getting from their atmospheres was contaminated, it was messy. And that's an emerging science question that needed a fast answer.
Okay, so once this fast-paced small sat gets into orbit, what's its actual to-do list? It's not hunting for new planets, so what is it doing?
Its job is purely characterization, calibration, really. The plan is to do a very deep very dedicated study of at least 20 known exoplanets. It's super targeted.
And it's looking for what, specifically?
The big three ingredients for an atmosphere. It's looking for signs of hazes, clouds, and the big one, water vapor.
It's funny, if you think about the James Webb Space Telescope as this, this giant all-seeing eye that can look at anything in the universe.
The ultimate multi-tool.
Right. Then Pandora is more like a specialized surgical instrument. It's built to do one thing over and over with obsessive precision.
That is the perfect analogy.
Yeah.
And the hardware shows it. Even though it's just the size of a fridge, they call it keen-eyed because every part of its design is about accuracy and stability.
So what's inside? What's the instrument?
It's a telescope with an 18-inch mirror that's about 45 centimeters. And for a small sat, that's a pretty serious piece of glass. It can gather a good amount of light from these pretty faint distant stars.
But it's not just taking pictures, right? That mirror is feeding the light into some very specific instruments. We need to talk about the two kinds of data it's collecting at the same time.
Absolutely. The whole package is designed for, and the mission states this, an extreme level of accuracy. So first up is the light spectra.
The rainbow of light.
Exactly. When a planet passes in front of its star, the starlight filters through the planet's atmosphere. And the atoms and molecules in that atmosphere, like, say, water, they absorb very specific colors, very specific wavelengths of that light.
So you get these tiny little dark lines in the rainbow, like a barcode.
A chemical barcode or a fingerprint. It's perfect. Pandora's instruments can read that barcode in incredible detail. And crucially, it's getting the fingerprint of the planet's atmosphere and the star itself simultaneously.
Okay, that's data type 1, the chemical fingerprint. What's the second?
The second is the good old-fashioned brightness measurement. This is the transit method 101. As the planet crosses in front of the star, it blocks a tiny bit of light, causing a little dip in the star's brightness.
And Pandora measures that dip with super high precision.
With incredible precision. That tells you the planet is there and how big it is. But the magic happens when you combine that precise brightness measurement with the chemical fingerprint from the spectra, both taken at the exact same time with the same stable instrument. That's the key to everything Pandora does.
This all sounds very methodical. It doesn't sound like a quick look survey. What's the actual observation plan? How long does it spend on each target?
Oh, it's incredibly patient. It has to be, because the signal it's looking for is just so faint. So after it launches, it'll spend about a month on commissioning, warming up, checking all the systems.
Standard procedure.
Right. Then it begins its one-year prime mission. And for each of its 20 targets, it is programmed to just stare. It will lock onto a star system and observe it continuously for a full 24 hours.
A whole day for one star. That seems like a really long time for a satellite. Why so long? Why not just catch the transit, which might only last a couple of hours?
That long stare is essential for fighting the noise. You have to remember, these stars are dozens, even hundreds of light years away. The signal, that little atmospheric fingerprint, is ridiculously faint. So by staring for 24 hours, you build up the signal. You can average out all the random instrumental jitters and flickers.
You improve the signal-to-noise ratio?
Dramatically. Plus, and this is critical for what we're about to discuss, it lets you watch the star itself rotate. You can map its surface. You get the full context, not just a snapshot.
And it does this multiple times per target.
It does. To make sure the data is rock solid, it will repeat that 24-hour stare 10 separate times for each of the 20 systems over its one-year mission.
10 times.
10 times. That repetition gives them the statistical power they need to be certain. It's the only way to defeat the main problem they're trying to solve, this thing called stellar contamination.
Let's get right into that, the stellar contamination problem. For someone listening who's really into this stuff, the basic idea of looking at light through an atmosphere seems so clean and elegant. The planet crosses the star, light filters through, you read the barcode. Simple. Why is it so much harder in reality?
The problem isn't the planet. The problem is the star. The light source is flawed. And this is a really fascinating and counterintuitive part of astronomy.
How so?
For a long time, the working assumption in these transit measurements was that the star was, well, a constant, a perfect, steady, uniform light source.
The ultimate reference point, a perfect light bulb in the distance.
Exactly.
Yeah.
A clean backdrop. But we know now that is completely wrong. Stars are not these immaculate, shiny objects. They are churning, roiling balls of superheated plasma.
Active.
Incredibly active. Their surfaces are covered with features. They have star spots, which are like our sunspots, cooler, darker patches caused by intense magnetic fields. And they have the opposite too. Brighter, hotter regions called faculae. The entire surface is a shifting, modeled pattern of bright and dark patches.
Okay, I think I see where this is going. So when a tiny little planet crosses in front of that star, it might pass over a nice, clean, bright part,
Or
it might pass right over a big, dark star spot.
And that changes everything.
Yeah.
That is the absolute core of what Daniel Appiah calls the stellar contamination problem.
How does that mess up the measurements so badly?
Think about it. We're trying to measure the tiny dip in light caused by the planet. If the planet passes over a dark spot, it's blocking an area that was already dimmer than the rest of the star. So the dip in total light you measure is smaller than it should be.
Oh, wow.
Your measurement of the planet's size is wrong. And worse, the spectrum of light coming through is wrong. The light from a cool, dark spot is redder. The light from a hot, bright patch is bluer. This messiness, this contamination from the star's own splotchy surface, makes the atmospheric data totally unreliable.
That's a huge problem. We're using the star's light as our baseline, our reference. But if the reference itself is constantly changing and flickering, how can you possibly isolate the tiny signal from the planet's atmosphere?
You can't. Not reliably. It means you might be seeing a dip in the spectrum and thinking, aha, that's water vapor.
When really it's just the signature of a cool star spot that was behind the planet during the transit.
Precisely. We were misattributing the star's noise to the planet's signal. As the data from Kepler piled up, scientists started realizing this. Appiah said, and this is a direct quote, "If you don't properly account for this stellar noise, all bets are off when you make claims about a planet's atmosphere."
Okay, I have to push back a little here. Surely this is a known problem. I mean, with an instrument as powerful as the James Webb Space Telescope, can't you just model the star's activity and subtract it out mathematically?
That is a great question. And yes, you can try to model it, but a model is only as good as the data you feed it.
And JWST doesn't have that data.
Not in the way it needs it. The source material is very clear that this stellar contamination problem absolutely affects JWST data. Webb has this unbelievable power to collect light and see faint spectral lines, but it's usually just taking a snapshot during the transit. It doesn't have the continuous multicolor context of what the entire star was doing at that exact moment.
So JWST can see the result, the final combined light, but it can't easily tell which part of that signal came from the planet and which part came from the star's surface.
You've nailed it. It can't disentangle the two signals. And this is where Pandora becomes the hero of the story. It is the very first space telescope designed from the ground up to solve this one specific problem.
The first one.
The first one. Appiah says it's the first mission really designed to study the stars and their planets together. It's not just looking at the planet. It's simultaneously creating a detailed, multicolor map of the star's messy face.
Okay, let's break down that multicolor aspect because that seems to be the secret sauce here. How does looking at the star in different colors solve the problem?
This is the really clever bit. Different stellar feature spots, faculae, they look different in different wavelengths or colors of light. A cool, dark star spot, for example, blocks a lot of visible light, making it look dark to our eyes.
But it might look different in another color of light.
Exactly. That same cool spot still glows brightly in infrared light. Meanwhile, the thing we're looking for, water vapor, has its strongest, clearest absorption barcode in the near infrared.
Ah, I get it now. It's a process of elimination.
It's a differential measurement. If Pandora sees a dip in the visible light from the star system, but sees no change in the infrared light where the water signature should be,
then you know the dip was caused by a star spot, not by water in the planet's atmosphere.
Precisely. By measuring everything at the exact same time across multiple color channels, you can mathematically separate the two signals. You can say, okay, this much of the change was the star being messy, let's subtract that out, and this little bit left over, that's the real signal from the planet's atmosphere.
It's like having two equations to solve for two unknown variables. Without Pandora, you only have one equation, so the answer is ambiguous.
That's it. It removes the ambiguity. It's not just a telescope, it's a diagnostic tool. It lets us finally trust the atmospheric data we're collecting, which is the only way we can move forward.
Okay, so let's place Pandora in the grand scheme of things. We've established it as this ultimate filter for messy starlight. How does a fridge-sized satellite play with the giants of the field, like Kepler and, of course, JWST?
It's not a competitor. It's a collaborator. It's maybe the most important collaborator they could have. Pandora is a context setter. It's a calibrator. It provides that missing piece of information that makes the data from those other missions more valuable.
So let's start with Kepler. Kepler was the mission that gave us thousands of those planets in the first place. How does Pandora help a mission that's already over?
It retroactively improves its legacy. Kepler was brilliant at finding planets. It was just looking for that simple dip in brightness. But it didn't have the tools to deal with this stellar contamination problem we've been talking about.
So a lot of the Kepler worlds that we thought might have interesting atmospheres, that data is suspect.
It is. So Pandora's target list includes some of these well-known Kepler planets. By going back and staring at them with its specialized instruments, Pandora will provide the first ever clean atmospheric data for those systems. It lets us finally interpret Kepler's amazing discoveries with confidence.
That's incredible. It's like an update patch for a past mission. And then there's the big one, the synergy with JWST. Why does the most powerful telescope ever built need help from a small sat?
This is maybe the #1 reason Pandora got funded. Webb's instruments are just breathtakingly sensitive, especially in the infrared where water signatures are.
But the star is still messy.
The star is still messy. If Webb observes a planet around a very active red dwarf star, which are prime targets, and that star pops off a flare or has a huge spot rotate into view, Webb's beautiful high-resolution data is still contaminated.
So let me see if I have this right. JWST gives us the raw, super detailed spectrum. It can see the depth and shape of those absorption lines like nothing else.
Unparalleled power.
But Pandora provides the correction factor. It's the key that tells scientists, okay, from that beautiful JWST data, you need to subtract the specific amount of noise that we measured from the star's activity, and what's left is the true atmosphere.
You've got it. It's a force multiplier for Webb. It makes Webb's data more powerful by making it more certain. The two missions together can do what neither could do alone. Pandora provides the clean stellar context, and Webb provides the deep atmospheric detail.
So the immediate goal here isn't to find life, is it?
No, not at all. The team is very clear about that. The mission is to find the foundational ingredients. Is there water vapor? And to perfectly characterize the host stars. You have to learn to walk before you can run. We have to be able to reliably measure the basics before we can ever hope to find complex biosignatures. Pandora is teaching us how to walk.
Let's shift from orbit down to the ground. This mission is led by the University of Arizona, the U of A. This isn't just a science project for them. They're actually flying the satellite. Where is mission control?
It's all in-house for them. The entire mission is being managed from the U of A's Multi-Mission Operations Center, or MMOC. It's located right there on campus in Tucson, in the Advanced Research Building.
That's a huge responsibility for a university. What does that actually entail on a day-to-day basis? It's not just downloading pictures, I assume.
Oh no, it's full-on mission control. They are responsible for everything. They plan and upload all the command sequences, telling Pandora which star to look at for how long.
So they're managing those 24-hour stares.
They are. They're tracking the spacecraft's orbit in real time. They're receiving all the science data and, just as importantly, all the telemetry.
Telemetry being the spacecraft's health data.
Exactly. Is it too hot, too cold? Are the power levels good? And they're actively managing the spacecraft's health, especially its thermal stability.
Right, you mentioned stability is key. Why is keeping a telescope at the right temperature so critical for this specific mission?
Because tiny changes in temperature create noise. The signals Pandora is measuring are dips in light of just a few parts per million. If the telescope's mirror expands or contracts by even a microscopic amount because of a temperature change, it throws the whole measurement off.
So the team in Tucson has to constantly adjust things to keep it perfectly stable.
Constantly. They have to keep it in a state of thermal equilibrium for that entire 24-hour observation. That's the only way they can be sure that the signal they're seeing is from a planet hundreds of light years away, and not just from their own instrument warming up.
This sounds incredibly complex. Does the U of A have a track record with this kind of thing?
They have a stellar track record, you could say. The director of their Space Institute, Erica Hamden, pointed out that this is a continuation of a really strong legacy.
What other missions have they run?
2 really famous and really complex ones.
Yeah.
They operated the Phoenix Mars lander.
The one that dug into the ice on Mars?
That's the one. And even more recently, and maybe more complexly, they ran the OSIRIS-REx asteroid sample return mission.
Wow. OSIRIS-REx just brought its sample back to Earth last year. That was one of the most complicated robotic missions ever attempted.
It really was. You're talking about navigating to a tiny asteroid, touching down, grabbing a sample, and flying it all the way back home. The fact that the U of A managed missions of that caliber proves they have the expertise and the infrastructure to handle something like Pandora. They've earned it.
There's another thing I loved in the source material, which was the structure of the team itself.
Yes. This is a really great aspect of the Pioneers program.
It's not just the seasoned veterans running the show.
Not at all. It's a key part of the mission's philosophy. More than half of the leadership roles on Pandora are filled by early career scientists and engineers. It's designed to be a training ground.
That's fantastic. So the people who are going to be leading the big flagship missions in the 2030s and 2040s, the ones that will be hunting for life,
are getting their hands-on mission control experience right now, flying a real orbiting observatory. It's an investment in the next generation.
And finally, this mission is all about creating a reliable foundational data set. Does that data stay with the team or is it shared?
Oh, it's shared. That's a core principle here. All the data Pandora collects, the clean spectra, the stellar noise maps, everything for these 20 systems, it will all be made publicly available.
So any researcher in the world can use it?
Anyone. It allows scientists everywhere to use this data to calibrate their own observations, whether they're using a telescope on the ground or reanalyzing old Kepler data or trying to clean up new JWST results. It's an open source solution to a community-wide problem.
So we're at the end of our deep dive, just as Pandora is on the verge of its launch. Let's try to pull this all together. For the person listening who's just captivated by this search for life, why is this one unassuming, fridge-sized satellite so important?
It's important because it's about the quality of our knowledge. For years, we've been in the census era, just counting planets, 6,000 plus. Pandora moves us into the characterization era.
From counting to understanding.
Exactly. It's the filter that lets us accurately read the chemical story told by a planet's atmosphere by finally removing the interference, the noise, from its own parent star.
That stellar noise problem really is the heart of it. The idea that stars are these messy, chaotic things, and that chaos was scrambling the tiny, faint signal from the planet.
It was. And Pandora's job, its one and only job, is to map that chaos in multiple colors at once so that we can isolate the true signal of the planet.
Without that, any claims about finding water or anything else are just built on a shaky foundation.
It's extremely shaky. Pandora provides the bedrock. It provides the certainty we need so that when we use a powerful tool like JWST, we can trust the results. I think Tomás Díaz de la Rubia from the U of A said it best. He said, "We're on the cusp of a new era in which we will, for the first time, peer deeply into the atmospheres of distant worlds."
That's a powerful statement. And it really speaks to the need for this kind of methodical foundational science. It's not always about the big, flashy discovery.
No. Sometimes the biggest breakthroughs come from fixing a fundamental problem in your measurement technique. The leap from knowing about 6,000 planets to truly understanding the atmospheres of 20 of them, that is a massive, massive step forward.
Okay, so let's leave our listeners with that final provocative thought to chew on. Where does this all lead?
All right, consider this. The ultimate goal, the thing we all want to find, is a biosignature, a sign of life, like oxygen, in the atmosphere of an exoplanet.
The ultimate discovery.
Right. And we now know of more than 6,000 potential targets. And here we are, investing all this time, money, and incredible engineering talent into a dedicated mission just to reliably confirm the most basic component, water vapor, and to clean up the starlight.
So here's the question for you to think about. What does the fact that we need a mission this sophisticated just to get a reliable baseline tell you about how confident the scientific community is that there are worlds worth studying out there?
They wouldn't be building this incredibly precise filter if they didn't think there were amazing things waiting to be seen on the other side. The investment itself is a statement of confidence in the abundance of planets and potentially water throughout the galaxy.
And if we start from that assumption that the targets are plentiful, then how does Pandora, combined with the power of JWST, change the odds of finding a true biosignature in our lifetimes?
It suggests the odds might be a lot better than we thought. But only if, and this is the entire point of the mission, only if we get the fundamental measurements right first. Pandora is our tool to finally get them right.
An incredible mission, about to begin a new chapter. Thanks for taking this deep dive with us.
It was a pleasure. I will definitely be watching that launch on Sunday morning.